I'm here to present our team from Master Institute and MIT. Our team aimed to redesign the wastewater treatment using with integration of nanowires and bio-electrochemical systems. So according to UAE annual report, the water consumption per capita ranks number 3, despite the fact that the natural rainfall is extremely low. So therefore, UAE has increasingly reliant on the unconventional water treatment resources. So here is the biggest wastewater treatment in Abu Dhabi. It has an average daily flow of around 360,000 per cubic meter. Here, this diagram shows the current state of the art in wastewater treatment. As you can see, each unit is dedicated to removing of one type of pollutant. It also requires special facilities for disinfection, such as chlorinations. Those facilities will require huge land areas. And also, their complicated processes has problems such as low conversion and high operating costs. The reclaimed wastewater can be used in many aspects. They can be used in industry for cooling of machines. It can be used in urban areas for irrigation of green land, or it can be used for car washing. But most importantly, around 74% of the reclaimed wastewater is used in irrigations. And this demand has doubled from 2008 to 2015. The nutrients in the reclaimed wastewater worth about $5 per cubic meter. This could save a farm around $200 per year in fertilizer cost. So here is our proposed water filtration process. So the wastewater we have is collected from the river. So the wastewater will first enter the bio-electrochemical systems. The particles, organics, and inorganics will be first removed by coagulation and bio-breakdown. After that, the superponent will enter our magnesium nanowires. Then these magnesium nanowires will remove heavy metals and organics. After these two stages, the water we expect to reach the irrigation levels. The third step is required for improve the water quality to drinking level. The titanium oxide nanowires under the UV light would have induced photocatalytic oxidation, which can decompose organics and kill bacteria. So we hope that with our integrated systems, we can reduce the overall cost by reducing these required units. Also, with enhanced facility and decreasing volumes, we can have a portable device. We can install them into individual buildings. So here I break down the preliminary results into these two parts. The first part is about optimization of bio-electrochemical systems. This part was done at Master Institute. This diagram shows the mechanism of the filtration processes. So the water enters from the side, and as it moves towards the center, it will get filtered. Those air are provided for the growth of the microorganics to break down the organics. So we have around 40 liters per day for 3 months. So here are the results. The blue column shows the initial amount of the elements in the raw wastewater collected from the river, and the gold column shows the amount after the treatment. The red curve indicates the standard for the unrestricted irrigation. This means the plant that can be eaten raw by human beings. As you can see, for those elements, we have met the standard. We're still working on the ammoniums. A second part is about synthesis of nanowires. Those are the optical image of the nanowires. The black one are magnesium oxide, the white one is titanium oxide. So they're very elastic, they just act as a sponge, so you can handle that with your hand. But if you look at it under the electron microscopes, they're really tiny. The diameter is around 10 to 100 nanometer. So compared to your hair, this is 700 to 7,100 smaller. So with such an enhanced surface area, you expect that those ions will be absorbed on their surfaces. So this is one of the example with hydrophobic coatings. They can absorb oils. And these magnesium oxide have shown exceptional removal capability towards heavy metals. Those are done at laboratory levels, but the concentration is pretty high, but we can still remove around 100% of lead, 95% chromium, and 91% of cadmium. So with both effort from the Master Institute and at MIT, we have developed method for the bio-electrochemical cells and the nanowire synthesis. By couple these two elements, we can see that we can filter the raw wastewater to the water that we almost meet the standard of irrigation, except one element, that's ammonia. We have to work on that. Going forward, we want to scale up the design for a pilot test. We want to run a continuous mode over months of operation to verify the system stability. We also will work on the titanium oxide, because our final goal is to meet the drinking level. And thank you very much. Here is our team, and we would like to extend our thanks to Marina, our catalyst, and the Dishbone Center. If you have any questions, you're welcome to visit our posters.
Thank you.